Hi, we will present Beyond the Pixel, a photometrically calibrated HDR dataset for luminance and color prediction. We live in a constant light field that directly affects our human biology. It has a high dynamic range of both natural and artificial light. We can try and capture this light field with a digital camera, but the pixel's relation to the physical light is lost in the complex and nonlinear ISP of the camera. We can go one step further and capture linear high dynamic range images as an HDR bracket, but the light is only represented up to scale. Conversely, to obtain photometric measurements, that is, the absolute physical light as perceived by the human eye, we need specialized tools such as the luminance meter that measures the amount of light in a given direction, and the chromometer that measures the integral of the luminance over the whole hemisphere. However, those tools are expensive and limited to expert users. Because of those limitations, computer vision research was inherently restricted in its ability to study the impact of light on humans. Can we bring photometry in the hands of everyone and go beyond the linear pixel? In this work, we present the first large-scale photometric HDR dataset that we hope will enable the community to explore new problems in photometric computer vision. We have the chance to have access to a high-quality dataset of over 2,300 HDR panorama images of indoor scenes, the Laval Indoor HDR Dataset. We aim to calibrate the original camera to adapt the dataset to photometric values. This is the setup used for calibration. The camera takes an HDR bracket of a scene, and a chromometer measures the true illuminance of the scene. The illuminance is then computed from the HDR as the weighted integral of each pixel. Repeating this process for over 120 scenes, a linear relation arises. Applying the slopes for each channel to the original dataset results in our novel photometric dataset.
Thanks to our photometrically calibrated dataset, for each scene we now have the absolute luminance value in candela per square meters, or nits, for each pixels, as well as the absolute color temperature value in Kelvin. In order to showcase the great variety of the light fields in our dataset, we have detected all the light sources in all of the scenes, and when showing a few examples, we can see that our dataset contains multiple types of light sources, ranging from bulbs to tubes to windows, with a great variety of parameters, including sources with a color temperature ranging from 2 to 9,000 Kelvin and a luminance between 50 to 600,000 candela per square meters.
Our novel and varied dataset allows us to explore data-driven photometric computer vision tasks. The new possibilities are many, but we focus on proposing baselines for 3 novel tasks. Let's share a few of our findings. In our tests, we compress the photometric image to an LDR simulating the large ISP degradations. Firstly, we aim to predict per pixel luminance. We found that the baseline unit produces results robust to ISP degradations. For the same unit baseline adapted to our second task, per pixel color prediction, it can learn the true color of the scene even when we augment the white balance of the input. This opens the door to white balance study under multiple illuminance. The third task is the prediction of hemisphere illuminance from a limited field of view. We observe that the RMSE worsens as the field of view is narrower. Finally, we experiment with generalization to another camera. To do so, we calibrated a point-and-shoot 360 camera and produced a smaller photometric HDR dataset. The experiments are run from the JPEGs directly produced by the camera's ISP. We find that fine-tuning is necessary to obtain good performance. Please see the paper for more details on the experiments. We hope to see you improve on those baselines and propose new photometric tasks. To help you with your research, both dataset and code are available right now.